We've already talked about the mean and the variance of sampling distribution for sums and averages. The last feature of the sampling distribution we need to discuss to put it to work for inference is the shape of the sampling distribution. And I've left this as a separate short topic, partly because of this amazing result called the central limit theorem, or CLT for short. This is an amazing theorem and a result that we'll be using quite a bit in the rest of the course, so it's important to learn its name and its implications. So when we want to look at the shape of a sampling distribution of the sum, one of the things for our inference work in a very introductory course is that we are interested in situations in which the shape of the sampling distribution of the sum is approximately normal curve. So yes, that's a big limitation, and it's something that in practice we're going to need to check, but that's where statistical theory started in the 1920s, and that's where we're going to start. In one sort of special framework, if the distribution of the x values we're measuring themselves is approximately normal curve, then the distribution of the sums is also going to be approximately normal curve. And so we saw in our work in week 3, with the help of Baldi and Moore, that things like heights and weights, when we specified men or women or specified age ranges, did approximately follow normal curve. And we had problems that looked at cholesterol values for men and women separately that followed normal curve. With a lot of study, we know that the lengths of human pregnancies are approximately normal curve distributions. Those are going to be the kinds of situations where we'll be able to say if the distribution of the x values themselves is approximately normal curve, then we know the sampling distribution of the sums are. And I want to emphasize that this will work for any sample size n, even very small ones like samples of size 25 or 50. And of course, when we start to use this in practical problems, if we're not given a lot of information like heights and weights and cholesterol values having approximately normal curve distributions, we'll learn how to use the sample data to check these kinds of claims so we can say something about the sampling distribution of the sum. So that's the first instance in which the sampling distribution of the sum will be approximately normal curve. Now there's another feature that I want to look at in this illustration, is to take a look at this population of heights of women ages 18 to 25. This is the population of the x values. It's in section 7 in the reader, and you can see that the boxes in the histogram do follow the normal curve quite closely. So we're going to take a look to illustrate the point we made in the previous slide at sums of samples of size 5 and 10, which are very small indeed. But here's what the illustrations look like. The box plot for a large number of sums really does adhere quite closely to the superimposed normal curve. It's even better for a sample of size 10, but we certainly would consider these as pretty small samples to be looking at this feature of the sampling distribution of a sum being approximately normal when the population is. So one of the things we have to distinguish in looking at the pictures on this slide is the distribution of the heights themselves on the left and the distributions of the sums in the two pictures on the right. But this is really a feature that sometimes does happen with real data, And it's a very nice way to know that we can use inference procedures assuming that the sampling distribution of the sum is approximately normal. So that's kind of the ideal case. There's another way we can get information, and this is really the kind of amazing part. If the sample size is large, then the sampling distribution of the sums is always approximately normal curve. And the kicker here is that this is true for large sample sizes, even if the distribution of the x values is skewed or has outliers. So this amazing fact that if the sample size is large, then the sampling distribution of the sum is always approximately normal curve is the result that's called the central limit theorem. Now Baldi and Moore just state this, and we're just going to state it in section 7.2. The CLT is what I'll call it for short. The proof takes some pretty darn elegant calculus. So we're going to rely on the shoulders of giants and talk about how to use this result. So here's an example to contrast with the previous one. This is a population of response times in seconds to a mental processing task. We looked at this example and the previous one in week 1 and week 2 and week 3. We saw something like this when we talked about densities of continuous random variables. So here it is again. This again is the histogram for the population of the x values. So we're now going to also look, as we did with the heights of US women, at sums of samples of size 5 and size 10. And this time, because that distribution is quite skewed, it has a long right tail, the sampling distribution for sums of size 5 really doesn't look like the superimposed normal curve. And even when we look at the same graph for samples of size 10, there's also quite a bit of daylight between the histogram boxes on the right and the superimposed normal curve. So I'm going to say that these distributions of sums show a pretty marked departure from the normal curve. Now if we continue to work with this example and we bring back the histogram for the population again, but this time we look of sample sizes 20 and 50, then what we're going to get is much better symmetric mound-shaped close to the normal curve distributions for the sums. But I would say there's still some departure from the normal curve even with a sample of size 50 because the distribution of the population is quite skewed. So these are going to be important illustrations. These aren't really mathematical proofs, but they're just two contrasting illustrations of what can happen to distributions of sums depending on the distribution of the population. So that was about sums. We also want to say something about the shape of the sampling distribution of the average x bar, and the distribution of the averages is going to follow exactly the same patterns as what we've been talking about for the sampling distribution of the sum, because x bar is just a simple linear transformation of the sum. So in conclusion, there are two situations in which we can safely assume that the sampling distribution of x bar is approximately normal curve. So the first one, the central limit theorem one, is going to be that the sample size is large. Greater than 100 is usually roughly okay. It's hard to get statisticians to commit on this because there is no magic number. The more skewness and outliers in the population distribution, the larger the sample to get this beautiful behavior for the x bars. And then in a very special case, if the distribution of the x values themselves is approximately normal curve. So we'll be using these results a lot in our work coming up in weeks 5, 6, and 7 especially. And we want you to be able to have this background about when the shape of the sampling distribution for sums and averages can be assumed to be approximately normal curve.